Let's take a quick look at an application of higher order derivatives. This is a very common physics type application. The position at time t of an object launched straight up at initial velocity of 25 feet per second from an initial height of 30 feet is given by f of t equals negative 16t squared plus 25t plus 30. You've seen this sort of a thing a zillion times starting in algebra. And very commonly, we would write this as s of t, where this is a position function. And s is very commonly used for to represent a position function. So what is the velocity at t equals 0 and t equals 2? Well, velocity is the rate of change in position. Well, the rate of change means a derivative. So what this is saying, and I'm going to stay with this f of t notation. I just wanted to note to you there that the s of t is commonly used for position. So what this is saying is that velocity as a function of t is actually equal to the first derivative of f of t. In this case, f of t is a position function, which is equal to, if I take the 2 down, I'm going to use the power rule here, this would be negative 32 t to the 2 minus 1, that's t to the first, plus 25t to the 0, which is this 25. So this is my velocity. So if I want to know how fast it's going, if I evaluate this at t equals 0 and t equals 2, I'll know at 0 seconds and 2 seconds. So v of 0 equals negative 32 times 0 plus 25, which equals 25 feet per second, which makes sense because we said that's the initial velocity. At time 0, that's where we're launching it. So v of 2 equals negative 32 times 2 plus 25, which equals a negative 39. Now that's kind of interesting. The initial velocity was 25 feet per second. Now 2 seconds later I'm at a negative 39 feet per second. Well, really this change in sign is really telling me that I am on my way down. Initially it went up, and at some point it peaked, and then it started to come back down, where like this is the initial height on a building that's 25 feet high. That's kind of the scenario. What's the acceleration at t equals 0? Well, acceleration is a rate of change in velocity, and velocity is the rate of change in position. So acceleration, a of t, is actually equal to the second derivative of f of t, which is equal to the first derivative of v of t, which I'm going to put up here. V of t we said was negative 32t plus 25. So if I take this derivative, I get negative 32. So the acceleration is a constant function, constant at negative 32. Well, these numbers are rounded. If you have any physics classes, you know roughly 32.2 feet per second is the acceleration of gravity at sea level in a vacuum and all that kind of stuff. So this is kind of confirming what you probably already knew from physics. And notice that a of 0, the initial acceleration equals negative 32, and likewise the acceleration 2 seconds later is also negative 32. Matter of fact, it doesn't matter what seconds you use, the acceleration is always negative 32. And really all that negative 32 is kind of telling us, if this is the ground here and if this is 25 feet high, and I launch this thing straight up and it kind of did this sort of a thing, that the acceleration is in this direction, because what's happening is gravity is pulling it in that direction. So even though I launched at 25 feet per second, it's slowing, which means accelerating in this direction. So let's go back just momentarily here, and I want to take f of t and I want to take v of t, and I want to plot those on the same graph, because remember the velocity is just the derivative of the position function, and we know how to interpret derivatives of a function. So I want to see if we can interpret this some way that makes sense. So back in Maple, I'm going to tell it, see, I'm going to plot curly brackets, and the original function was negative 16 t squared plus 25t plus 30. And then my acceleration, my velocity function was negative 32t plus 25. T equals, say 0 to, I don't know, let's go 3 seconds to see what it looks like. And then I'm going to use t and y axis. Y equals negative 2 to, say, I don't know, 40. I'm just going to guess how high I'm going to go. So let's make the thickness something I can see. Okay, so what is going on here? Well, here's my position function. I originally launched it at a height of, I was drawing 30. I was drawing 25 on the graph. The initial height was 30, but the initial velocity was 25. So those earlier graphs that I drew right here, this should be, actually that should be a 30. I got some numbers turned around there on it. And likewise here, this should be 30. 25 was the initial velocity. I got those ideas turned around. So what is this thing telling us? Well, here's my position. I started at 30 feet. I went up to 40. Wasn't a bad guess. I went up to 40-ish, came, and then I started coming back down. Now, notice if this is the velocity, I'm going to change this. I want my y to go a little bit lower, so I'm going to go down to like negative 20. Yep, need to go farther than that. How about negative 50? There, that's a little bit better. See, if this is my velocity, notice here that the slope of the tangent line on this curve is horizontal at this point, which means the rate of change of this function is 0. Well, the rate of change of a position function is the velocity. So if this is the velocity function, sure enough, velocity is 0. See, it started out at 25 feet per second, and because of the force of gravity, the velocity slowed down, slowed down, slowed down, slowed down, slowed down, until it stopped at the top, which is 0. And then it started down, and then the velocity was very small, but negative. Remember, velocity, it has a direction to it. Well, we want to talk about vectors right now, but velocity has a direction, so we can have a negative velocity. So that means I'm simply coming down the other direction. So the velocity is increasing, 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 and then at some point, roughly in here, it hit the ground. So the function keeps continuing, but the physical phenomenon stopped. And we could actually, if I carry this out far enough, which it looks like I'm pretty close, if I found this value right here, I could tell you how fast it was going when it hit the ground. And also by looking at this, just roughly, I'm not going to calculate it. You could do it with algebra. But it looks like it hits the ground at roughly 2.75 seconds-ish. So, just as we did earlier in other functions, we just took the original function, the derivative of the function, and we tied the derivative into what's happening on this function. And this time is kind of extra super cool because this has a physical phenomena that we're actually modeling. This is a position of something that was launched upwards. This I think is really kind of cool because this shows where the tangent line is 0. Well, you know that's where it stops. So at that split moment, it had no velocity. It was motionless as it started in the opposite direction. And that's what this line again is saying, is the velocity was 0 for that instant. Kind of cool.